Hello everybody, in this video I'm going to go over an application of the derivative, which is marginal analysis. I will define or actually review some definitions and then I'll do some examples, okay? Well, first off, marginal cost is the cost of producing one more unit. Marginal revenue is the revenue of selling one more unit. And marginal profit is the profit of producing and selling one more unit, okay? I guess I was going for a Mardi Gras theme here. Whatever. Anyway. So for example, if I have that C of X represents the cost of producing X units, then marginal cost is, well, marginal cost will be, cost is equal to, well, if I have C of X plus 1, that is the cost of producing X plus 1 units. But I don't want to know the cost of producing X plus 1 units. I want to know the cost of producing that X plus 1 unit. Okay, not X plus 1 units, but the cost of producing that one more unit. Okay, so then if I want to know the cost of producing that one more unit, I have to take the cost of producing all of them and then subtract the cost of producing the X previous units. Okay, so what I'm saying is, for example, cost of producing unit number 11, right, will be equal to the cost of producing exactly 11 units, and then you subtract the cost of producing 10 units. Okay, perfect. Okay, now I started this video saying that we were going to use derivatives to compute marginal analysis. Now the question is why? So let me tell you why. Let me give you the intuition, right? So if you think about it, so suppose that this graph represents cost. So this is cost of producing X units. So then again, my X-axis is the number of units, so units. And then my Y-axis is just cost. Cost of producing X units, okay? Now, if here, say I have, I'm just going to do it in general. So say here I have X, and this is X plus 1. Then obviously, this is the cost of producing X units, and this is the cost of producing X plus 1 units, okay? So if you think about it, then since marginal cost is just C of X plus 1 minus C of X, then you can think of it like the slope of the secant line, okay? So then marginal cost, it's actually equal to, well, C of X plus 1 minus C of X all over X plus 1 minus X. So in other words, it's just the slope of the line, of the secant line, going through X C of X and X plus 1 C of X plus 1. So then the idea is, approximate marginal cost, right, with the derivative. In other words, with C prime of X, okay? So what I'm saying now is that from now on, the marginal cost, that cost of producing the next unit, will be approximated by the derivative at X, okay? At the previous one. Make sense? First example, we have to assume that a demand equation is given by Q equals 8,000 minus 100P. Find the marginal revenue when the production level is 1,000 units. Okay, so we know that marginal revenue, we're going to approximate marginal revenue by taking the derivative of the revenue function. So before we do anything, we need to find the revenue function. Now we know that the number of units, which in this case we're using Q to represent it, the number of units is the independent variable, okay? So before I get started, before I find my revenue function, which I know revenue is equal to P times Q, where P is price and Q is the number of units, and then again, the number of units is the independent variable, I'm going to have to go here to Q equals 8,000 minus 100P and solve for P first. Okay, so before we get started, we have to solve for P first. So we're going to solve Q equals 8,000 minus 100P for P, okay? The way I'm going to do that is by saying, well, I know that that means that 100p it's equal to 8,000 minus q. Divide by 100 and you get finally that p is equal to 8,000 divided by 100, which is just 80. I'm going to erase this and write 80. So 80 minus q divided by 100. Okay, so now I know that p is just 80 minus q divided by 100. So I can use that information to write my revenue function. So then I know that revenue it's equal to p times q, and I know that p is equal to 80 minus q divided by 100, okay, times q. So the only thing I did was to plug in what we had for p here from this step, okay, from this step, okay, perfect. So now that I have my expression and I know that I'm going to have to take the derivative of it, I'm going to write it so that it's easier to take the derivative. So I'm going to distribute that q. I get that r is equal to 80q minus q squared divided by 100. So now that I have my revenue function, I can find marginal revenue. So we know that marginal revenue is just equal to the derivative of my revenue function with respect to q, which is the independent variable, the number of units. And r is just a difference, and I know that I can take that derivative by going term by term and using the power rule. So the derivative of 80q is just 80, and then the derivative of negative q squared divided by 100, I know what to do. I take that exponent, I bring it to the front, right? I take that exponent, I bring it to the front, and I get that this is just minus 2q divided by 100. So I will simplify this, okay? So I know that it'll be negative q divided by 50. So I'm going to erase this and write it as negative q divided by 50. So now that is my marginal revenue. If I want to answer the question, which is what is the marginal revenue when the production level is equal to 1,000 units, meaning when q is equal to 1,000 units, I just plug it in. So I get that. That tells me that marginal revenue for q equals 1,000 is r prime of 1,000, which is equal to 80 minus 1,000 divided by 50. And this is equal to, well, I have 1,000. I should be able to do this in my head. So I get 80 minus 20, we get 60. Now, what does that mean, okay? What does that mean? Because we're saying that this is an application. So if I get the marginal revenue when the production level is 1,000 and I get 60, what does that mean? So the interpretation is, so that tells me that, I'm going to write it up here. The interpretation is that revenue of selling the next unit, so unit number 1001 is $60, okay? So keep in mind that marginal anything means it's the cost of producing the next unit. It's the revenue of selling the next unit, or it's the profit of producing and selling the next unit. Okay, so let's do one more example. So now we have that the demand function for a product is P equals negative 0.025x plus 900, where P is the unit price and X is the quantity demanded. Okay, so keep in mind that some people use X to represent the number of units, some people use Q, I use both, okay? And we have to find marginal profit for X equal to 5,000 if the cost function is equal to 200X plus 280,000. Okay, so let's do this. So I don't know if you realize that this example has multiple parts, okay? So if I want to find marginal profit, I have to find the profit function first. So then again, whenever we're finding marginal anything, you have to find the actual function first, and then you take the derivative of it. So then let's find profit first. Well, we know that profit, I'm going to use P for profit, it's equal to my revenue minus cost, right? It's equal to revenue minus cost. Now here, we don't have the revenue function, but we know what P is, right? We know that P is equal to that function, and we know that revenue is always equal to price times the number of units. minus the cost function we do have, 200x plus 280,000. Okay? So now I know that what I have to do is I'm just going to say, well, this is equal to P, which is negative 0.025x plus 900 times x, and then I have to distribute that negative. I'm going to get minus 200x minus 280,123. Okay? So let me take this and move it a little bit to the left so you can see the whole thing. Perfect. So now again, I have to simplify this a little bit more. I get negative 0.025x plus 900x minus 200x minus 28, 0, and then 1, 2, 3. Now I have to simplify this, okay? Let me simplify this. So I'm going to use my calculator. Of course, you can do it also. Make sure that we'll get the same answer. So here we go. I get negative 0.0. Oh, this is squared. Oh, beautiful. Okay, so then this is negative 0.025x squared. And then that I can do in my head. 900 minus 200, I get plus 700x minus 280,000. Okay. So I'll give you a second. So we did revenue minus cost, and that took me to this expression, this quadratic expression, which is negative 0.025x squared plus 700x minus 280,000. Oh my God, I don't know my numbers in English. 280,000, okay? Perfect. So now that I have profit, I'm ready to compute my marginal profit, and I know that marginal profit, my marginal profit is just the derivative. So it'll be P prime of X. And I know how to compute the derivative of a summary difference. Just go term by term. So this is just negative 2 times 0.025, okay, which is just negative 0.05. So here we go. Negative 0.05x. And then I get plus 700. And then the derivative of a constant is just equal to 0. Okay? So that tells me that, let me use a different color for this. So that tells me that the marginal profit when x is equal to 5,000, it's equal to P prime of 5,000. So this is equal to negative 0.05 times 5,000 plus 700, which is equal to, I'm going to do it, negative 0.05 times 5,000 plus 700, I got 450. So I get 450, and beautiful, okay? Very good that you can follow the steps and get a number, but the main thing here, the reason why we're doing this is so that we can interpret this, okay? So what does that mean? What does it mean that the marginal profit is equal to marginal profit when x is equal to 5,000, it's equal to 450, okay? So if that's the case, if the marginal profit when x is equal to 5,000, it's equal to 450, that tells me that that is the profit of producing and selling next unit, 5,001. So that tells me that profit of producing and selling unit number 5,001 is $450, okay? All right, so I hope this makes sense. I'm not gonna lie to you, you're gonna see a lot more of marginal analysis. I only did 2 examples with very simple functions, but we're gonna look at how to find derivatives of more complicated functions, and this will be everywhere, all over the place, okay? All right, see you next time.